Hello and welcome. I am Melly Annamalai, a product manager with Oracle, and my colleague Jayan Sharma and I have put together a couple of interesting use cases with graph analytics. Graph analytics is a hot topic these days because it enables you to get new insights into your data by analyzing the connections between your data items. So, what is a graph data model? When you model your data as a graph, you represent your data entities as vertices and any relationships between them as edges. For example, if you're modeling your customer data set as a graph, customers become vertices in your graph when they're naturally the data entities, and relationships between them or between them and other types of data entities become edges. For example, if you have products vertices in your graph, every time a customer buys a product, that becomes an edge. In an example from banking, if you have a financial transactions data set with accounts and information about cash transfers between these accounts, your accounts naturally are data entities and become vertices in your graph. And every time there's a cash transfer relationship between two accounts, that can be modeled as an edge. So any logical relationship can be modeled as an edge, which means that almost any data set can be modeled as a graph. So a graph gives you the ability to explicitly represent these relationships and consequently the ability to run graph pattern queries and graph algorithms on your data. So here are some examples of what you can do when you model your data as a graph. You can look for patterns such as cycles. Like, is there a cycle in my graph? A cycle might denote money laundering because a cycle in the financial transactions example I was just describing might indicate that money is moving around in a cycle. It's moving between different accounts and coming back to the source account. So that's a pattern you can identify when you model your data as a graph. You can also use graph analytics to identify specific sets of vertices that are more tightly connected to each other than to other vertices in the graph. For example, customers who have similar buying patterns and similar behaviors would likely be more connected to each other in a graph. So when you analyze your data as a graph, you can identify these communities of users, which helps you make better product recommendations to them. And path analysis is another very interesting example of what you can do with graphs. In manufacturing or network data management, path analysis can be used for what if types of analysis, like what happens if a node goes down? What happens if the design of a component is changed? In financial transactions, you can use that to identify things like here's an account that I'm suspicious about, and I would like to find all the cash transfer paths that originate from this account. So these are just a few examples like finding patterns, finding subgraphs, finding important vertices as defined by which other vertices a vertex is connected to, and so on. So these types of analytics can be are made possible when you model your data as a graph. So let's look at how you would use graphs to detect fraud. So here are two examples, or two tables. You have a bank accounts table with account ID and other customer information. And then you have a bank transactions table, which has a row for every cash transaction that's been made between accounts. You have the from account ID information, to account ID information, the amount information, and so on. So we can use any technology to identify answers to questions such as, is there a transaction between these two accounts? Are there accounts which have had no transactions, and so on? But like I was explaining just now, when you want to look at more complex patterns, when you want to look for cycles, when you want to look at paths which are, say, 4 to 7 hops away or any other variable number of hops away, when you want to do such when you want to run such queries based on patterns, based on reachability, and so on, and that's where graphs really shine. And that's where graphs analytics brings you added value. So let's take those two tables and see how you would create a graph from those tables. You have the accounts table, you have the transactions table, and every time there is a cash transfer transaction, as you can see here, from account ID 1 to account ID 672, that can be modeled as an edge. And every account in your account bank accounts table can be modeled as a vertex. So here you have an edge that goes from account ID 1 to account ID 672. It has a property of associated with it, that's the amount of the cash transfer, and that information is coming from this column here. So column values often become properties for vertices and edges. So each row in this accounts table is going to become a vertex, and every time it's a cash transfer, you build an edge and you associate the properties with these vertices and edges. So here's another edge that you're building for this transaction between account ID 2 and account ID 833, and you can build up your graph this way. So in the Oracle Graph feature of Oracle Database, we support the property graph query language, and you'll see some examples shortly in the demo. And this language includes DDL syntax for creating a graph. So once you've identified your accounts table, your edge tables, your vertex tables, and so on, and the relationships between them, you can use the DDL syntax to say, this is my vertex table, these are my edge tables. For each edge, this is my source vertex column, the destination vertex column, and so on. And once you specify this information, the graph is created for you. And when you're using the Graph Studio feature of Autonomous Database, some of this can be fully automated. The Graph Studio feature includes a graph modeler that automatically identifies the vertex tables using primary key information and automatically identifies edge tables based on the foreign key relationships between these tables. Now let's use this graph to run a few graph queries and graph analytics. So here is the Graph Studio console of Autonomous Database. And I'm going to log in here to my Graph Studio console so that I can start running some graph queries and graph analytics algorithms on the graph that I have. I've already created this graph using the vertex tables and edge tables example that I was showing you earlier. And I'm going to use this bank graph here that's stored in the database. I'm going to load it into memory because we have this in-memory graph server for high-speed graph analytics and graph queries. So I'm loading this data set into memory. And now that that's done, you can see here it succeeded. I'm going to go into notebooks and open up this Oracle database notebook that's here and start running some graph queries. So we have 4 interpreters that you can run with that you can use with the Graph Studio notebook. The Markdown interpreter, the interpreter to run PGQL, the property graph query language queries, to run algorithms in Java, and to run algorithms in Python. So let me start by running a simple query here. And I have mentioned that the property graph query language is a SQL-like language. And by that I mean it has a select clause, the from clause, and the where clause that you'll see an example of shortly. And also, and in addition, it has the ability to specify a graph pattern in the match clause. That's what makes it a graph query language. So this is a simple query which is basically saying select all edges. So select all edges that connect any 2 vertices, which is sort of like select star from tab that you might run on a database table using SQL. So here, because I limited it to 10, I've retrieved a few of the edges. I can go into the visualization tab here to select what I want to display. I want to have an account ID visible as part of that results display. And for the edge, let me have something that describes what the edge is, which is transferred. So you have the account ID information and the transfers label associated with the edge. So now let me run another query. And this time I'm going to look for, a more interesting pattern. I'm going to look for 3-hop cycles. So I start with A, so anything in parentheses is vertex A, transfers to B, transfers to C, and then transfers back to A. So that's a 3-hop cycle, and I'm going to find 10 such 3-hop cycles in this graph. And you can see here the 3-hop cycles that are identified in this graph. And now let's see, let me remove this limit. So I guess there are more 3-hop cycles in this graph. So let me see whether I can select them all from this financial transactions data set. And I can see here that a whole bunch of 3-hop cycles are available here. And here I can see here there's some interesting examples where money is being transferred within the same account. And I can look and say, okay, 872 is an account ID. So I right click on that vertex to get the properties for that vertex, and account ID 872 is transferring money to itself. Here, this account ID 88 that's transferring money to itself. So this is interesting information about my graph that I can identify by visually examining the graph. So let me now run a different query where I'm going to look for a 6-hop cycle. I'm going to start with account ID 1. So I'm introducing the where clause here. So I'm saying start with account ID 1, where V1 dot account ID equals 1. Start with 1 and go through many different vertices and come back to V1, the same vertex. So this is a 6-hop cycle that I'm looking to find. Is there a 6-hop cycle that starts with vertex 1 and then goes through a bunch of other vertices and comes back to 1? So let's once again go in and visualize the account ID information as well. You can see you start with 1, it goes to 259, 387, and then moves back to 1. So because I'm looking at 1, for some reason, maybe I have some other reason to examine account ID 1, and now I see that account ID 1 is transferring to 259 as part of this cycle, I might want to look at what's happening with 259. So maybe this is an interesting account. So let me see whether there are 6-hop cycles that include 259. So, and here we can say, oh wow, that is a lot of 6-hop cycles that are available with 259. So 259 is clearly a very interesting vertex for what I'm trying to uncover about my data set, because it's going through a lot of, it is part of a lot of 6-hop cycles. So that is very interesting. And now I want to run a graph analytics algorithm, and I'm going to run the PageRank algorithm. The PageRank algorithm gives me a measure of the importance of a vertex in a graph by looking at who it's connected to. So it's not just how many vertices you're connected to, but who you're connected to. And if the vertices that this vertex is connected to are important, then this vertex also will get a higher importance score. So the PageRank algorithm returns a value between 0 and 1, which becomes an additional property in the graph. So let me now go back to this query and rerun this query so that the PageRank property is available with this particular visualization. So once I do that, I can then use the PageRank value to do some interesting visualization operations on this graph, so that I can immediately look at which are the interesting other vertices. So let's say I add a highlight, and I'm going to add a condition, and you can see here that the PageRank value is now a property of the graph after I ran the PageRank algorithm. And I'm going to say, find me all vertices, or I want to say color, I want to find me all vertices which have a PageRank value higher than 0.0035, and give me a different color and size, so that I can, when I visually look at the graph, I can see that these are the vertices in the 6-hop cycles that are part of account ID 259 that have a high PageRank value. So these might be vertices that I might want to investigate further. So graphs also give you a way to visually look at your data and kind of visualize some of these patterns. Now I'm going to run one more query here, where again I'm working with 259 because I'm suspicious of that account, which is involved in so many cash transfer operations. And instead of looking for cycles, I'm just looking for paths. So this is the reachability analysis. I'm starting with this vertex, and then I'm saying 1 to 6 hops away. So you can see here that the dotted line indicates that there is a path 1 to 6 hops long from account ID 259. This is what I'm examining because I'm a little suspicious of it. And you can see here all the other accounts in the path that have a higher page rank value as well. And now let me go back and look at a customer example. So in this customer example, this is PaySafe, an online payment solutions company. They're interested in identifying anomalous patterns in their cash transfer operations by their customers. So you can see here on the left, you have a source account and a destination account, and lots of cash transfers happening between them, going through a number of intermediate accounts. So this to them is something that they need to investigate further. Why are these cash transfers going through intermediate accounts instead of being directly transferred to a destination? On the right is another anomalous pattern where we have lots of cash transfers happening, but relatively few source and destination accounts. So that's again something that they would like to investigate further. So they've been using graphs for a while now, and they're able to do these operations in under a second, something that used to take hours or days when they did this manually. Now let's move on to the next demo, recommending products using graph analytics. Here we start with three tables: a customer table, a movie table, and a cost sales table. The customer table, the customers are data entities. So each row in the customer table becomes a vertex. And similarly, the movies become vertices. So each row in the movie table becomes a vertex. And cost sales contains information about which customer rented which movie. And that's the relationship between these two vertices, and that becomes an edge in the graph. So you're modeling this graph as customers, movies, and who rented which movie. And this is the same data set that is used in the movie stream workshop for the Converse database. So you might have attended, you might be listening to that session as well, and there's a hands-on lab as well. So in this demo, we'll follow the whom to follow algorithm, which is typically used for social network analysis. So what happens here is you use the algorithm to cluster users based on whom they follow. And depending on which cluster you belong to, you can make recommendations for whom to follow based on the popular folks that are followed on social media by other members of the cluster you belong to. We can use the same algorithm for product recommendations. We cluster customers based on the products they buy, so that you can make recommendations for customers in a cluster based on the products that are popular within that cluster. So now let's switch over to the demo. So we start here with the PGQL query, and here we are just basically running a simple query where we are saying select all movies that Ricky Rogers has watched. And it's not really all movies. I mean, I'm limiting it to 10. So you can see here the match pattern, CEM. So find me all movies that Ricky Rogers has watched. And we can go in here once again to the visualization tab and select the property that we wish to display here. So we're displaying the movies that Ricky Rogers has watched, and this is Ricky Rogers properties. So this is a graph where the edges and vertices have a lot more properties. So then we can run another interesting query, which says, okay, now I'm going to take a look at Ricky Rogers and Blanca Diaz and see what are the movies that both of them have watched. So this is just to kind of show simple examples that are of PGQL queries. So these are the movies that the two of them have watched. So let me go into the settings here again, and here I will choose first name so that we can see here we have Blanca, we have Ricky Rogers. You can see Blanca's watched a lot of movies, and Ricky Rogers. So this is what we call a bipartite graph. You have two types of vertices, and you can then do analytics on this graph. So this is a graph where we're just saying, okay, here are all the movies that both Ricky and Blanca have watched, and this is the match pattern that specifies that you have M representing the movie vertex, and then you have edges on these customers pointing to this particular pointing to these movies. Now, to run the home to follow algorithm, let's first get a handle to the graph in memory. And here we run this, we execute this Java snippet to get a handle for the graph in memory. And you can see here that this is a graph with nearly 9,000 vertices and nearly 1,000,000 edges. And now I'm going to run a code snippet that would be the home to follow algorithm. So you can see here I am selecting a vertex, the vertex object for the customer Ricky Rogers, and here I am running the algorithm home to follow. And this algorithm returns two lists. One, a list of customers belonging to the customer that Ricky Rogers belongs to, and Ricky Rogers is a customer of interest here. Because that's whom we have selected here. We selected a vertex of type Ricky. We selected the vertex corresponding to the customer Ricky Rogers, and that's the vertex we're passing in as an argument to the home to follow algorithm. So the two lists that are returned to us are one, a list of customers in the cluster that Ricky Rogers belongs to, and then the movies that customers in this cluster like. So now that I've selected those lists, let me now print out those lists. So you can see here I can I'm printing out the names of customers who belong to the same cluster as Ricky Rogers, the customer that we're examining here. So let me switch to a tabular view. So we get a bunch of customers who belong to the same cluster that Ricky Rogers does, and we can take a look at the movies that customers in this cluster like. So let me open a new paragraph here and run this query, which would tell us the list of movies these customers like. So here we have the list of movies. So we can just run a few more PGQL queries to kind of get to pinpoint a few more movies that we want to recommend for Ricky Rogers from this list. So we can take a look at the movie Captain Marvel. So I'm selecting, I'm identifying whether with a PGQL query whether Ricky Rogers has watched this movie Captain Marvel. And we see that he has not, because we return an empty result. And then I'm going to take someone else from the cluster that we had. For example, Sang Hoffman here. I'm going to see whether Sang Hoffman has watched this movie. And we see that Sang Hoffman indeed has watched this movie, and multiple times. Captain Marvel has been watched multiple times by Sang Hoffman. You can see Sam Hoffman here. So perhaps this is a good movie to recommend for Ricky Rogers. So we can similarly look at another movie here. This is Toy Story 4. And we see here that Ricky has not watched Toy Story 4, but other members in his cluster, such as Sam Hoffman, have watched Toy Story 4, as we can see here. And again, he's watched it multiple times. So this means that this is probably a good recommendation for Ricky Rogers. So this is an example of how you can use graph analytics to make product recommendations. Let me wrap up this video by summarizing some of the key features of Oracle Graph and the property graph feature that we used in the demos that we showed here in this video. The key point is you can create a graph from database tables. There is no need to move data into a separate specialized database. You can create a graphs right from your tables in Oracle database. And you can take advantage of the in-memory graph server, which is part of the graph feature of Oracle database. For extremely fast graph analytics and graph queries, we have published benchmarks to show that we scale to billions of vertices and edges. We support the property graph query language, a SQL-like query language to find patterns in graphs. And we support over 60 pre-built graph algorithms. We saw two in the demos here today. We used the PageRank algorithm while working with the financial transactions graph, and we worked with the Whom to Follow algorithm while making product recommendations. And all of this is built on the enterprise capabilities of Oracle. And when you use the Graph Studio feature of Autonomous Database, you also get the automated graph modeler, the notebook with integrated visualization, which is what we used in our demos today. So Oracle Graph can be deployed in an autonomous database in Graph Studio, which was what we used in the demos today. It can also be used in any co-managed environment in Oracle Cloud, or if you're using Oracle Database in any other environment, or user-managed on-premises databases as well. In short, Oracle Graph is available anywhere where Oracle Database is available. So we hope you'll get started with graph analytics. Here are a few resources for you. Our webpage, we have a whole bunch of live labs, the Ask Tom series, we have a blog with examples and tips, and also a YouTube channel. So thank you very much for listening.